I need a legalese to get out of the way first, and the disclaimer is that this talk, you know, the opinions expressed by me, Fred, and Sanj are our opinions and not those of the organizations we currently work for or have worked at in the past. So that I had to get that disclaimer out of the way. I'm not going to spend too much on this. This is a standard slide. You'll see it from various presentations. The only thing I want to say is the motivations that are above the line are external factors pushing organizations to look at scale out of the grid and more compute power. What I liked is the below the line are internal factors that people are now looking at. And there was a talk I attended, so I pinched the middle one, which is risk muscle, which I quite like the term. And it is about using risk as a muscle to progress your business instead of it being a function you just have to do, which is why, you know, this scale out and the streaming engines become more relevant. Very quickly, this is I mean, we've worked for various institutions, and this is a distillation of generally how risk engines are put together. There's a grid, there's a workflow engine, there's potentially a caching layer. So it could be a database, could be disks, could be an in-memory cache, trades coming in, output going out. Won't dwell on this, but the rest of the talk will be built on this image. So, you know, that's why this is there. I'll hand over to Robert, a colleague from Google, and on the Dataflow presentation piece. Thank you.
Hi. So there's going to be a bit of jumping back and forth between each of us, so hopefully it's all going to make sense at some point. Just as a kind of why Google in this space and working together with these chaps, essentially Google has a quite long history in data processing, big data management. And the particular part that we're going to look at today is Dataflow, which is, well, we will come onto it, but think about stream and batch processing in a kind of a unified model. So to kick that off, I thought let's start with a little bit of history. This is Flume Java. So if you think about MapReduce, MapReduce is great. I mean, it abstracts a lot of the complexities of trying to talk to different systems and actually doing that distributed compute. But if you try and think about doing multiple MapReduce jobs, then you kind of get into the space of like a pipeline, a data flow, a directed acyclic graph. This is basically what Flume Java is about. It's about taking those steps and bringing them together. So that graph, if you want to conceptualize it, is kind of an orchestration, but important in terms of orchestration here is let's say the arrows on the graph. This is your collection of data. It's immutable and it's parallelized, so it's not just on one machine, it's sharded across different machines. So this is part of the background that's going into Dataflow itself. The other part is Millwell. So Millwell is about streaming. So it's about complex event processing, doing this at low latency. Again, there's a graph involved, but I guess the key concept here is that, you know, there is an unbounded collection. You have to look at that collection at a particular point in time, and the latter part of the talk, we're actually going into some details there. And the other thing is that there's going to be state involved here as well. So whereas the previous, you can kind of think, well, I've got, you know, an immutable collection. I'm going to do some functional programming. I'm going to pass from one stage to another. In this particular state, we have to think, well, because I have an unbounded collection, I have a stream coming in. When am I actually going to stop and look at something and actually calculate some kind of result? So these two kind of come together and they form Dataflow. Now, Dataflow was basically an effort that we made to kind of bring these together in our cloud space that we had an offering for customers, and they could basically look at either batch or streaming for a single API. So if you think about the type of calculations, the work that they're going to do, like filtering, grouping, these kind of things, think about MapReduce kind of tasks, I mean, they're all quite simple primitives, but if you think that I want to be able to do this on both a batch and a stream, or I like to look at this a little bit differently, both bounded and unbounded data, and we'll come back to that concept later, but essentially bounded data, think about it, you know, I have a field and I've closed the gates, all the animals in the field, I can basically count them, none of them are going to go in and out of the field. If I open those gates, I've got to have some way of knowing, like, am I looking now? Has an animal left the field and a new one's come in? Is it the same one again? So it becomes a little bit more complicated. But the type of work, the type of questions you might be asking your data at a specific point in time, a specific window, will be the same. So this was Cloud Dataflow. And in our effort, what we basically wanted to do, if I go back a few slides here and say, look at this history. So a lot of our history before we were in the cloud space was about producing research and white papers. And this wasn't just research and white papers. We were implementing these systems internally. But you'll see some big names up there like MapReduce and GFS. This is basically externally is the foundation of Hadoop, which is a separate effort to actually do this. But it's based on a lot of research that was done at Google. As we moved into the cloud space, what we saw more and more is like, okay, it's great that we're getting this research out there and people are developing this, but we can also take the efforts that we're developing and actually externalize them very early on in the process. And that way we have a programming model, an API, which everyone can go and use. And then the equation becomes a little bit different. From a cloud point of view, as a service provider, we're looking at providing a managed service to actually host and run that API. And that's going to become quite an important theme here as well. So I'm just going to go back forward again. So we're going to come now to Beam. So Beam is essentially the programming API. We took Dataflow and we donated it to the Apache Foundation, and it became Beam. The name is, well, batch and stream, Beam. There we go. A lot of thought went into that one. Naming things is actually a very difficult effort, and we'll save that for another talk. So I'm just going to let you have a quick snapshot of the Beam model before I hand over to Fred. But essentially what we're going to be focusing on here is we have a programming model. So this is the API, this is the abstraction. This can be implemented with different languages. We have languages such as Java and Python, and we're going to focus heavily on Java today. And then we have a number of runners. So basically, where's this going to run? So Cloud Dataflow is our managed service, is one of these runners. Another runner could be Spark. Another runner could be Flink. So if you imagine you have one API, one abstraction that you're actually programming against, and then depending on your environment, what you have available, the cluster that you want to go and run this on, you can actually go and use that as your runner. And we will talk about some of those differences and the pros and cons of doing that later in the talk as well. But now I'm going to hand over to Fred, who's going to talk a little bit about Beam.
This is forward.
Yeah,
Yeah.
right.
Yeah, so as Robert mentioned, Apache Beam is basically an abstraction over top of the Dataflow model, and that was contributed by Google and its partners to the Apache Software Foundation, which became Beam. So the cornerstone of the Beam API is the functional approach, which is known as a do-fun, so otherwise known as do-function. Right? It takes an immutable set of inputs, which is a P collection. So these data elements are then applied against a function, which can have one or more outputs. So what happens is the DAG, the graph, is analyzed by the underlying runner. It will optimize how the functions are actually operated on. So you can see here, so we've just said do fun A, B, C, D, but it could be, for instance, loading static data, loading market data, combining it, and then applying maybe a calculation at the end, for instance, in do fun D. Another part of the API is the parallel processing. All right, so by saying the par do or parallel do, you apply this against the functions and it will run them in parallel. So what's interesting about Beam is you don't control where the stuff gets run. You don't control the parallelization. You don't tell how to serialize the data. Instead, the underlying runner does that for you. So it kind of gives a little bit less control to the programmer, but actually you're concentrating more on the functions and how you apply them to the data elements, which it's a lot less code and it's a lot less work. So one interesting aspect of this is the underlying runner can do optimizations for you. So for instance, in Dataflow, there's a concept called fusion, where it can see the opportunity to apply two functions simultaneously in memory. It'll keep them, it'll distribute it to the worker for you, and it'll run it in memory, which is a lot faster. So this is opposed to things like maybe Spark or older models where you have to tell it to apply a particular function again on a particular worker. And what that does is people found that it was a lot less efficient, or the programming style became difficult to follow. So eventually they would copy-paste all the code together and back into one function, which is actually against the functional style. So I'll go back to Robert for Dataflow.
Yeah, so as I just mentioned, Dataflow is a runner for Beam. So this kind of puts the emphasis, what do we need to do with a runner? What can we possibly offer in that space? So you think you're programming against your API, you're telling it what you want to do, your functional programming style. And then when it comes to actually running this code, well, this high-level architecture here will give you some kind of overview. I mean, there's a part which is compute and storage, there's a resource management part. This is how Dataflow does it. Another runner may do this in a different way. That's actually up to the runner how it wants to implement that. But when we're looking at Dataflow, then we can look at some of the optimizations or some of the added non-functionals that we can bring. So non-functionals, for example, scheduling and monitoring. No one wants to go and spend their time doing that. So if we wired all that in, and that's actually going to our logging systems and our monitoring systems, then you can actually get that information without having to make that effort yourself. I mean, essentially all you need to do is like log your errors and output your messages. Another part is graph optimization. So we just saw one version there about Fusion. Here is we might actually split those functions up, or we might change the order of those functions in order to give us the best optimization. And it very much depends on what you're doing. So that optimization is really actually looking at the Apache Beam programming model and seeing how those things can be combined. And there are ways to actually go and break something like Fusion, for example. So we might say, well, actually, by fusing two things together, I'm not getting the best performance. So you would add a group by key in between to actually force those to separate. But in most cases, what we're looking to do here is actually go and find the most cost-efficient way of running this. So auto-scaling is an interesting concept, and I will point to something that Dataflow, the service, does. So Dataflow, if you can imagine these workers running, when we're actually doing the shuffling stage, we will actually use a separate memory shuffle service that we have to go and do that. So it's kind of we have a separate service. Those workers, they need to do a shuffle. Instead of having all those workers like broadcast to each other what they need to do, imagine they kind of offload that to a memory service, which does the shuffling and then pass it to the next stage. This is really useful because it really allows us to kind of scale out and scale down. So the idea with Dataflow is essentially that you can kind of put your foot on the gas pedal and just say how fast or slow do you want to go. And then there are some cost considerations being made there, but if you take it a little bit simply, then it could be something like, I could use 2 workers for 10 hours, or I could use, 5 hours with 4 workers, just to give you some indication. But in order to do this, if you think about that auto-scaling process, you've got this notion of work being done on those individual machines, and some of those machines might be straggling. This might be because one key is particularly hot compared to another, so you have slight skew in your data, for example. And because of that skew, the other keys that were going to get processed by that machine are now backed up. They're waiting. Whereas other workers, they've actually gone through their work. They're finished. They're waiting around. So before we go and say, hey, add more workers, we need to be able to say, well, actually, if I kind of chop off those straddlers and like reshuffle them around, so the rebalancing my work, I can get a better utilization of my resources. So it's not just about adding extra resources to get things done quicker, but it's about looking at the most cost-efficient way of actually running that. So
I think it's worth pointing here that if you've got so in the context of most people here, if you've got a population of plain vanilla flow instruments and you've got Bermudan swaptions to go with it, that's the context in which one is taking 20 minutes to price and one is taking 300 milliseconds to price. That ability to dynamically rebalance, if you've got 4,000 cores deployed and you're doing a mixed population of 300,000 trades across this population, that ability to rebalance the grid without you having to do any work at all is quite impressive to look at, without you having to write a single line of code. I think that is the context I just wanted to bring in.
So I think now we're gonna switch pace a little bit, and we're gonna look at actually what we're calculating, what's the work that we're doing. So as we mentioned before, the programming model here, we're using Java. So we're going to actually now focus on the world of quants and the languages they use and how actually to do that work. So I'm going to hand over to Fred.
Okay, thank you. So this is the sort of the guts of how we ran a lot of these risk functions. So the typical setup is that you've got your C++ pricing library, and as we mentioned before, the container is Java, so it has to have a way of calling the C++ functions. That's going to be via JNI. So this is the Java layer that helps us access C++ functions. So there's a couple challenges here because Dataflow and Beam aren't really designed for this type of workload out of the box, right? So this is one of the first times this has ever been used this way. So one of the interesting things was that basically if the C++ causes some sort of access violation or seg fault, what happens is in fact the container will fall over, right? So obviously that's not a good thing. So what Google Engineering suggested we try was, why not call it out of process? So actually start up another JVM and run the JNI and the C++ in that manner.
It's worth pointing out that in batch mode, the fallover will happen 4 times, and then the batch will get abandoned. So if you're running an overnight batch, your batch won't complete. And if you're running it in streaming mode, it will keep attempting it forever, so somebody has to go and manually kill your batch. So
Yeah.
both cases are undesirable cases. So how do you get around that?
Yeah, exactly. So so Google mentioned to try and run it out of process, and also it's important. They mentioned to try and follow a dead letter pattern. So what this means is, I'll go to the next slide. What you'll do is your calling process will watch the exit signal of the spawn process, right? So basically, we need to figure out a way to pass the parameters to the outer process call now, because it's no longer in the same process. And we decided on using standard input as a starting block. We also realized that, in fact, passing all these parameters is simply an interface, right? So it's an interface object of some sort. You pass in the entire thing as a pricing context, and then your outer process call can perform all its work. We also found that using disk was a very effective way of achieving that. So what you do is you write the output of the worker container process becomes the input of the external call. Also, conversely, the C++ will write its output to disk, which is read back in by the Java process. And as you can see here, so the process signal is watched by the container process. If it dies, what happens is you'll be able to tell that there's some problem with your calculation.
Again, it's worth mentioning that the disk here is a Docker container running across thousands of physical or virtual machines. And so the disk happens to be that local container that, it's not some NAS that you're wiring to.
Yeah. Yeah.
I think also just to emphasize again, like in this particular setup, the quant code here is in C++. I mean, I guess this is a common theme to everyone, and now we're trying to use a Java processing framework, because that gives us good semantics on how to actually work with the data, how to distribute the data, so that functional programming model. But yeah, you need this way to actually kind of actually say, go run this calculation with this data. So when we put the disk in between here, essentially, I think one of the things you mentioned before, Raj, was that if you think about these libraries in C++, there's a lot of noise potentially, because they might be your own libraries, they might be slightly older libraries, they might be libraries dependent on third-party software. So there's a whole bunch of messages being sent on standard out, and if you're listening to all of that stuff, you're kind of like, okay, which part is my data? So by kind of like abstracting and saying, okay, we're actually going to store the data here on disk, and we're just going to wait until that process is finished, then we've actually made that easier for ourselves. Now, there's a big question then, does the disk interaction slow this down? But we will come back to that.
So if you're using a third-party XML parser, for example, and it is spewing out a whole bunch of logging messages out, you can still send that to Stackdriver and trace your logs, but you can separate that out from your output results, your risk or your PV that you're calculating by making that C++ call. So that separation is quite neatly achieved by going through that disk process.
So we want to also mention the serialization framework that we chose. Now, you don't have to use it, but we chose protobuf. As you can see, it supports a lot of different types of languages like Java, C++, Python, etc. So what it gives us is it'll generate the bindings for you. And what's important here is you can use a consistent sort of programming style and API, right, across different boundaries without writing lots of code. I think each one maybe uses 2 or 3 lines of code to both serialize and deserialize that data. So it's a very effective way of crossing these language boundaries. So yeah, just in here, all we've done is basically show that the protobuf is what we've written there. And so it serializes to disk, as we mentioned, and then the output is, again, read back in by the Java process. So one of everybody's favorite topics is testing. So what the protobuf gives us is the ability to have the output of our unit test in the Java side become the input of the unit test on the C++ side. So what this does is actually really effective, that you separate the IT team's use cases from the quant team use cases. And especially, I think, in production, this is where it becomes very useful. You can actually output this protobuf context to somewhere like your database or a file system. If there's a problem during pricing, which is, every once in a while you have to have some of these problems, right? What happens is you can just pass that protobuf to the quant team so they can debug it. You don't start up big UAT systems, databases, message queues, all that stuff. They just use their C++ main method and they can run the protobuf. So we also realized, interestingly, that once you can do an out-process call with C++, actually you can do it with any language. So using the Beam API, you could call Go, you can call Python. And so this is in the context of running your workflow using Java. Python is also supported by Apache Beam and Dataflow out of the box, so you can write the entire thing using Python API. But it has a few limitations on the things like windowing, and its API is maybe not quite as advanced usually as the Java one.
Yeah,
it is catching up though.
Yeah, the API is trailing a little bit, but essentially, if you were, let's say you were using C and Python, then you could say, well, actually, do I want to use Java for this orchestration? In this case, I just want to emphasize that the protobuf really gives you that abstraction. So the point you made of like being able to go and store that data from the different stages somewhere in a key value store, and then kicking off like for an individual trade that maybe we don't understand that library again. We have that segregation of responsibility. We have that separation, which allows for testing. And yeah, protobuf is a very compact serialization. So great performance. We'll see a little bit about that later. And also, again, working with different languages. I mean, it's just literally creating those bindings from the language, and the protobuf libraries actually provide you with the tools to actually go and create those bindings.
So this is the final view of it, basically. So our container process sends the protobuf to the C++, so our pricing context goes in. Output can be, as I said before, one or many. So in the case of our risk output, we may have errors. We also can catch any sort of uncaught exceptions from the C++ process. So I want to talk a little bit about the Beam module separation. What Beam lets you do is it abstracts out the different data sources and sinks by using what they call I/O connectors. So with very little code, basically you can set up both inputs and outputs to your pipeline code and functions. In the case, for instance, you may have a Kafka queue that you're reading from, or an Elasticsearch data source. It may output from your pipeline to Redis or MongoDB. And then conversely, you can swap them around, and you're reading from MongoDB, outputting to Kafka or Elasticsearch. So it's a very important part because this stuff is handled more, we feel, by the IT team. So reading in from a data source of some sort, like your market data, your trade data, the quant teams maybe can handle more of the functions that you want to apply during your pipeline. So yeah, like I said, it gives a nice clean separation again. So I'm going to hand over to Sanjeev to talk about Apache Flink.
Thank you very much, Fred. Right, so I'm going to talk a little bit about Apache Flink. As Rob mentioned earlier on, there's different runners in Apache Beam. So you write your code in Apache Beam, you run it in the Beam API, and you can give it to Google Cloud Dataflow, or you can give it to something like Apache Flink. So that gives you the portability, doesn't lock you into any particular runner. So Apache Flink is an open source processing framework. It grew up completely independently of Google Cloud Dataflow. So the company behind Apache Flink is called Data Artisans. A few years ago, they said, hey, we like the Beam API. We think that's going to be a big player going forwards in this space. So we're going to make Apache Flink compatible with running Beam jobs. So write your Beam job, run it in Cloud Dataflow, and run exactly the same code in Apache Flink. So as you say, code written for Beam can run in Apache Flink. So let's get back to how do we actually build this risk engine. So hopefully by now, all of you are hooked on this stuff, and you're wondering, okay, we've got this risk engine. How do we actually start experimenting with it, building it in-house? So with Flink, go to the website, download Flink, install it on your machine, and you can use that for the distribution and the workflow. On the left-hand side, as Fred has talked about, you can use MongoDB as your I/O connector. So you don't have to worry about any other complications in terms of running different sources. So for what we've done, we use MongoDB, but you can use Redis, you can use a JDBC connector, any type of source will do. Running Beam. So as I've mentioned, your Beam job runs on Flink. No code changes. Obviously, if you're using MongoDB on premise in your data centers and you're running with, let's say, Bigtable in the cloud, you'll have to use a different I/O connector. We won't go into the details of what the code looks like. However, we hope to come back and talk about those idiosyncrasies. we write our results to disk just to make things easy. So as part of the work we've been doing, this was set up on a customer's premise. We were taking trades, taking market data, running our risk engine jobs, and writing our results to disk. So if Flink and Dataflow can kind of do the same thing, why not just use Flink? Now, Flink is not a managed service. Cloud Dataflow is. So with Flink, you have to configure and scale everything. So as potentially many of you work for financial institutions, acquiring hardware, the expertise to actually run these technologies at scale is not a trivial task. So you could, if you wanted to, run all of this on premise and not worry about all the cloudy type stuff. However, it's a non-trivial exercise to do this. And if there's one thing you take away from Flink versus Dataflow, just remember Flink is not a managed service and Cloud Dataflow is. And if you go down the Flink route, you will have to go do all the work to configure and scale. So, doing it yourself in your own data center, you can install Kubernetes, use Mesos, or some other kind of orchestration or virtualization technologies. Personally, so when I was doing this, I used Ansible because we couldn't get any of the other tools to work in our environment. So it was a fairly low-tech system. If you don't want to do it yourself, what could you do? Phone a friend. So Rob's already talked about the Google Cloud experience using Google Cloud Dataflow. You could install Flink on the Google Cloud platform. Not sure why you'd want to do that, but you could do that as well. On AWS, you can use Elastic MapReduce, so Flink is supported on that. And in Azure, you could probably use a Kubernetes engine in Azure to install Flink and run that at scale as well. So again, many different ways to run Flink. It's, I guess, a little bit more flexible in terms of what you can do. If you still really need to run on premise for security reasons, you can't get your data to the cloud yet, I would strongly advise you to look at the Data Artisan's DA platform. So I guess there was a similar slide shown a little earlier about Cloud Dataflow and the logging and the metrics, etc. So this is not an open source piece of software, the DA platform. This is something you have to go to Data Artisan's, pay for it, and install it on your machines. But this offers some of the kind of monitoring and stuff which no one really wants to create in a bespoke manner. So if you really want to run on premise, take a look at that. And I don't work for Data Artisans, by the way, so it's, I'm not getting paid for plugging them. Okay, during development, what do you do? So if you've got Beam and Flink, and you've got your MongoDBs running, you can actually drop MongoDB. So as Fred has mentioned, with the I/O connectors, you can just pretty much go to disks. So you can start this up on your machine. Anyone who's Docker aware can just do a Docker pull Flink, write the Beam jobs, and just run everything on your machine and not worry about all this fancy cloud stuff, which, you know, is always going to go wrong. No, I'm only kidding. It's all great. Okay, during testing, you should use the cloud. So even though I've said you can run your Beam job, run it on Flink, take the same code and run it in Dataflow, there are differences between the runners. So Fred mentioned Fusion, Rob mentioned the straggler. So if you've got one node with lots and lots of queued requests for, let's say, Bermudan swaps, it will rebalance that for you. Flink won't do that for you. So Cloud Dataflow gives you a lot of a value add on top of what you can get from Flink. So some of the actual differences between the two are, in Cloud Dataflow, you need a bunch of jars. In Flink, you need an Uber jar. Not a huge problem, but you have to make sure you kind of build your DevOps to make sure you can package for each environment and test and actually do some kind of back testing as well. Another problem, Flink will decide the parallelism for you. So it will say, okay, how many machines do you want to run this across? How many cores do you want to use? Dataflow will do that for you. So this reminds me a lot of writing JavaScript code. So when I used to write JavaScript code, I'd write it for Internet Explorer way back. But it doesn't guarantee it's going to run in Chrome or Firefox. So when you write your Beam jobs, you have to make sure it runs everywhere in whichever environment you're running. And with that, I'll hand back to Raj, who's going to talk about the tests we've done with Flink and Dataflow.
Thank you, Serge. We'll come back to the Flink theme at the end as to why we, even though the title is Running Analytics with Google Dataflow, why we spoke at length about Flink. So we'll say, I think Sanj just touched upon it, but we'll come back to it. So here are some results. The left-hand side is the XML JNI results. The right-hand side is the protobuf results. And what I'm trying to highlight here is that if you look at the blue bars at the top, which is the left and the right-hand side, it's Dataflow. There is not really that much difference in Dataflow performance when you switch from XML JNI to protobuf, because internally, Dataflow is optimized for XML. When you try and do it on premise and you use unoptimized parsers for XML, when you switch from protobuf, from XML JNI to protobuf for Flink inside your data center, you will find that there is a reasonable difference between your performance of your grid when you switch to protobufs. And the good news is that Flink in your data center begins to compete very, very well with the performance of Dataflow in Google Cloud. So yes, you don't get the auto-scaling, you don't get the managed service, but if you want to start a journey where you have a legacy estate and you've got to move it to a streaming paradigm, but you can't move the estate and move to the cloud because it's too many moving parts, you can de-risk it in the full knowledge that you can have a stepwise approach, go to Flink, make sure that the paradigm works, you get the same risk and P&L numbers that you do with your current engine before you commit to moving to the cloud. You become cloud ready in that sense when you start on this journey. I think Sanj mentioned, why would you run Flink in Google? You could take that paradigm further. You could say, I will run Flink and Beam on premise. I'll get my results. I will run Flink and Beam in Google Cloud as my next step, and then I'll move it to Dataflow as my next step. So you can actually go down that journey to move to Dataflow in that incremental fashion, so that you keep your moving parts. It is production systems. You will get screamed at if it goes wrong. So you can sort of control the risks by moving in that incremental manner. If you're doing Flink in Google land, you will use a tool called Dataproc, by the way. That's all I want to say about the batch results here. There is a lot more detail behind this, which it is 7 o'clock on a Tuesday, which I don't want to bore you with. I think that the main point here is that you get to a paradigm where you can get on-premise performance as good as you can get in the cloud. This is the scale-out characteristics when we did, this was a combined population. We were doing, so this was only for plain vanilla swaps. It was 2 million plain vanilla swaps. And what happens, what I want to highlight here is that in our case, we were using open source quant analytics, and the interest rate curves were built from FRA futures and swaps. The interest rate curve is being bootstrapped in the C++ memory every time you make a outer process call. So you find that there is a flattening of that scale out when you go beyond, let's say, 4,000 cores. If you really want that to be linear all the way to 16,000 cores, you have to start looking at your data structures, at your quant libraries, and can you serialize your bootstrap forwards and discount curves in advance and start sending that discount curves with your trade population? You might find that the linear characteristics of the scale out is different. So I think particularly for quants who will now control the workflow and will see the data structure, the influence of the data structures that you use with your C++ code, you get a very direct feedback loop as you change your data structures and you see your scale out. If you do this in the cloud, you can get that scale out very quickly. You can do it on premise and see how linear you are and at which point you become nonlinear. And I think that what we find is the amount of code you write is literally dozens of lines of code to achieve this. The amount of code base you get to achieve this is really small.
Raj can also mention, so when you're doing this testing, all you're doing here, you're not changing any code, right? The interesting part is we literally would just change the number of vCPUs on a particular machine, the number of workers it's using. So you can run this by literally just changing parameters. So again, because it's a functional approach, right, all you're focusing on is what functions are you applying against the data elements, right? So I think that was a very cool thing. So.
And the fact that Sanj mentioned you must test in the cloud is because that dynamic rebalancing characteristics you get with a managed service, which you can try and achieve it on premise, but good luck to you. I think it's a lot of effort, which it's easier to buy in. So that is the end of our. So far we've concentrated on batch. So because we were talking about analytics and data structures and the focus was mainly the B part of Beam. So now we go to the EAM or the streaming part of Beam, and I just want to introduce the concept that you've got market data that is changing, and conceptually if you have I think Robert will introduce this concept better, but you have this concept of event and processing time, and let's say you've got a book of 30,000 swap, it's $1 book, and you want to price it every 2.5 minutes, because you can actually price it every 2.5 minutes. You can start windowing your population of trades on a fixed window of 3-minute intervals. And really the concept is, if during that 3 minutes, if some of the trades change, how do you value those trades that have changed during that 3-minute interval and merge the windows of your book valuation? So you're valuing it on a book key versus the values you get on a trade key. How do you merge them back? And so this is work in progress at the moment. There's a lot of thought that needs to go into this, but I'll hand over to Robert to introduce the concepts behind windowing.
Yeah, thank you. So we're going to go through these questions, but I guess it's worth pointing out at this point, we've done the batch testing and we've started to work on the stream testing now and seeing okay, how can we actually get this to, let's say, closer to real time? So as things are happening, when do we want to actually emit a result and tell the world, this is going on? Then you have to start thinking about the semantics surrounding your code. So let's break this down. I mean, there are kind of 4 questions. What results are you going to be computing? Where in event time are these results calculated? So let's think event time is when that actual thing happens. In the real world, something happened, and we want to do something with that. But we don't get to see it in event time. We get to actually handle that in processing time. This is the moment where I'm going to say, right, I've seen that event, and there is a lag between those two. I mean, if you could eliminate that lag, then you potentially make a whole bunch of money, I guess. And then it's like, how do these refinements relate? Now we'll come back onto that last piece, that last question a bit later, because that's where it starts getting a bit complicated. So first of all, what are you calculating? So let's do something simple. Let's sum integers per key. So we have keys, let's just call this our trade key, and we just basically want to add up the value, or whatever else. Here you can imagine your do farm where you're actually going out and calling that out of process quant library and say, here's my trade, go and calculate the value of this trade. And then you get it back, and maybe you're going to aggregate this. So there are different things you can do here. But for example, here we're just going to keep it to, we're going to sum the values for a particular key. So if we were to do this and run it straight away, essentially what we have is a global window. Once we've processed all the data, we can emit a result. So event time here at the bottom is when these trades actually occurred. The processing time is how long it actually takes us to actually go through and price all these trades. And then we're going to aggregate them, and we get to some number at the top there, which is 51. Once I've finished all my processing, I can tell the whole world, hey, the total is 51. So can we do that a bit, can we be a bit more clever about that? So we can start splitting this up into windows. In this particular example, we're going to use fixed windows. There are different types of windows you can use as well. There are fixed, there are sliding windows, there are session windows. When you think about a session window, for example, it's an inactivity in event time between 2 things happening. This is very common in the online world, where someone's on a website clicking around and suddenly there's a pause, and you think, okay, now I want to kind of, emit some kind of result. I want to tell the world what happened with that user in the last 10 minutes. But for now, we'll go on to fixed windows. So we're going to fix windows of 2 minutes. And these are on the event time axis. So basically, we're going to split the event time now into 2-minute windows. Now, if we don't actually trigger this, and we just trigger this as a global window, so we don't do anything clever with the triggering here, essentially, we'll split that up. We will get a value for each window depending on where the trade actually happened, in which moment of event time. But we need to process all the data before we can emit a result. But now we're not going to emit one result. We're going to emit 4 separate results, one for each window that we're looking at. So we've broken it down, but we still have to wait until we've done everything before we can emit a result. This is still batch. This is still effectively bounded data, although we've broken it into windows. The next thing that we need to introduce is this kind of triggering. So we want to actually emit the result of that window at a point in time. This is what we do here is trigger at the watermark. The watermark is our interpretation. This is, let's say, some of the more difficult stuff. Our interpretation when we've actually seen all the given events for a particular event time, a period of event time. So this dotted line here, this is the ideal watermark. This is basically saying there is no lag in the system. I can process things as quickly as they happen. Well, that's not the case. So imagine that we're actually consuming data from a queue here, from a messaging system. I need some way of actually talking to that messaging system and all the processes that come after, or the code that you're running after, of actually understanding when I can trigger when that watermark is occurring. So if you look at the far right of each window here, this is when we're actually trigger it. So when that watermark actually passes to the next window. And then we will say here, now we don't have to wait until the end of processing. As soon as that window, this pane fires, we can actually say, right, I have 5. And you can start admitting these results out. So we can say, within that window, for this trade population, for example, I now have a total of 5, a sum of 5. And within the next window, I have a total of 22. But it's a problem here, and that's that 9 up there. That occurred, if we look in event time, that occurred at 12:02. But we didn't actually receive it due to some lag until 12:08. So what do? Do we just forget about that and just leave it? I mean, you could do. You can also talk to the system how you're actually going to work with that data. So that's the next part. That's how do these refinements relate. So in this particular, let's look at the late firings, and we're going to accumulate the data in the panes. So essentially what we will do, we will emit the result 5 when that pane fires, but then we will also trigger again later to say there's an update in this pane, and then we will give the result again a 9, and we've accumulated the results. So we actually retained that state, we retained that 5, and when we got that trigger later, we said, okay, 9. So hopefully that gives you a kind of idea of some of the stuff that you have to do when you're trying to do this in a streaming context. So you're looking at your unbounded data, you're splitting this into windows, and then you're deciding for yourself how you actually want to work with those windows, when you want to trigger them, and how those interactions, if things come early or things come late, what you're going to do with them. You can accumulate, you can retract, you can accumulate and retract together. So there's a whole bunch of stuff you can do there. But hopefully this gives you an idea of what's possible. And this is the stuff we're working on now. And as Raj and I were discussing earlier, this is the kind of stuff that maybe we'd like to come back later and actually show you this piece working, what it actually means in a streaming context. So I will hand back to Raj for the closing piece.
I think the only thing to remember here is that when we do trade pricing, you've got your market data, which is orthogonal to your trade streaming coming in, also moving. So you have to make some fundamental choices. If I'm going to value my book at time t, am I going to value the entire book with a consistent set of market data, which is at the beginning of that window? And then am I going to superimpose an edit to a trade within that book at the time using the market data relative to the time that trigger event happened for that trade? Because you might have a situation where you have a 100 million notional swap, which is novated to 40 million, and somebody may be interested in knowing the change in PV's breakdown between the change in PV due to the change in notional and the change in PV due to the change in market data. So if you need that breakdown of your PV change in terms of market moves as well as the effect of novation, you have to put a lot of thought into how you're going to design your emission, your triggers, your composition, which, like I said, is work in progress, right? We are still working on it, and we would like to come back and talk about it when it's in a more refined state. so the conclusions are there is some reference. I mean, the standard Beam reference. There is a special. So Reza has released a piece of code last week, which is now publicly available to run. This is a Hello World program in C++. You can see how the call is made from Beam to C++ in Hello World. It has all the elements for you to then plug in an analytics if you want to. So it starts very simple, but it has got some very core important concepts, which is really worth looking at. And please feel free to make Jira requests in that GitHub if you have issues and you've got other things you would like out of it. So the main emphasis here is that there are multiple runners. There's one API. And the runners are Alibaba, JStorm. So you've got a cloud. You want to run it in Alibaba. You've got JStorm. You've got IBM Streams. You've got and the number of the family of runners that will run Beam is only increasing. So we think it's a very powerful API. We have done a lot of work to separate out the I/O part from the actual pipeline construction. And that is not a trivial task. It has taken us 4 iterations to really refine that technique. We have not gone into that code because of lack of time, and it is quite heavy stuff. But if you, the one thing you will notice when you actually go through a standard word count tutorial on Beam, it takes a Shakespeare passage and does a word count on it. It doesn't show you how you would separate out your MongoDB I/O to your Oracle database I/O to your Bigtable I/O. So there is some clever techniques in Beam and supported by Google through pipeline options that allows you that separation. Happy to speak to people individually if they're interested more in that space. But that is the end of the talk. That is our conclusion so far. Thank you very much for listening.
So we're also going to stick around for some questions. Are there any questions that we want to do while we're still online before people have a chance to grab a beer at the back? So let me repeat the question and explain the chuckle. So the question is this: like you're running Dataflow in the cloud. Dataflow runs on Linux machines. So the question was like, can I use a different operating system to Linux? Can I use Windows, for example? And why would you want to use Windows? I'm guessing I'm preaching to the converted here, but you'd want to use Windows perhaps because you want to kind of show the results are actually the same as what you're already doing now because you're using Windows compilers compared to Linux compilers, and there are differences in numerical values, and when you're talking about very big things and very small things together, they tend to become quite annoying. The answer: can you do that with Dataflow? No, it runs on Linux. And essentially Beam, if the runner itself is Linux based in the cloud. If you want to run Flink, the test that you guys have done so far, that has been on Linux as well. You are exploring other options. I would put a big caveat here and say that it's perhaps a good opportunity to consider, whether you want to run your stuff on a Linux-based system. That's my personal opinion. I will defer to Raj for a more elaborated opinion.
Short answer is yes, you can. The Apache Beam has a thing called text.io, which was only supporting the Linux kernel till last year. There's a version of Apache Beam that came out from 2.1 which supports text.io on Windows operating systems. How scalable this is going to be, how stable this is going to be, we ourselves are experimenting. We don't have the answers yet, but the short answer to your question is yes, moving analytics from Windows to Linux is not a trivial task. And if you're itching to have a go with Windows, but you will be restricted to Flink and Beam. So you'll have to run Flink as the runner, and you will not be able to run it in Google Cloud. You could run it in Google Cloud by spinning up Windows machines in Google, so you can do your own stuff there. So yeah, the short answer is yes, you can, but no promise on the scalability and all the other characteristics we talked about.
I think also it's like Apache Spark. I think you can run it in Windows, but it's not recommended or supported. I think that's basically how it's put.
So essentially it's here how you kind of trigger the watermark. I would say it really depends. I would say if you're working in a streaming mode, you should start wrapping your head around the idea that things aren't necessarily complete. That is the whole nature of being unbounded. If you're looking for a bounded scenario, then there is nothing to stop you from saying, hey, I'm going to orchestrate this batch to run when all my data is being collected and trigger that. That would be a simple approach. You could definitely look at having fixed windows that capture that time for you as well, or do something like a sliding window which overlaps. But I mean, if I was advising someone and they said, look, I've got a bounded situation, I say, like, how often do you want to run this? I mean, like, yeah, we want to run this every hour, for example, or every 15 minutes. I mean, what kind of time interval?
So I'm thinking more about...
So a question here would be, how do you know when the data is complete? So what signal do you get?
So that's what we'll
Okay, so the question here, just for everyone else online that is perhaps listening, I hear there's like 10,000 people online now. So the question is basically, all right, I want to be able to run like all the time, but I want to actually trigger something happening. So this is very much the area that Raj and I have been speaking, and Fred, we've been speaking about these recent days, and it's basically saying, okay, what is that trigger? Now that trigger might be market data being refreshed, for example. That trigger might be something from another system. So essentially, you've got different inputs here. One of the concepts with Beam is side inputs. So what you could basically say is, I'm going to actually the window I'm going to trigger on something like a pub sub event, so a messaging event that I receive, and when that's triggered, that will be my first point, and then I'm going to use those side inputs at that time to go and do my processing. So it's really kind of understanding what's going to trigger that. Yeah, I would be happy to discuss that even, further with you. And actually, I think that's one of the things that Raj is keen to propose as a follow-up talk in a few months, for example, when we actually start looking at different ways of what are we going to react to? Are we going to react to trades coming in? Because they're essentially, depending on the size of your organization, they could be coming in all of the time. Are we going to react to market data changing? Or both, perhaps? Are we just going to have one pipeline, or are we going to have multiple pipelines? And then how are you going to serve that result to the user as well? So you might say, well, actually, I'm going to take snapshots of market data and just price all my trades and serve them up constantly to the user so they can actually see, based on this snapshot of market data, what's happening. You might have a parallel pipe there saying, as soon as the market data is refreshed, start repricing everything and show those deltas. So there's quite an area of exploration there.
So when you look at windows, there is fixed windows, there is sliding windows, there's session windows. I wanted to go to session windows first, and I've been discouraged by various people to start with fixed windows, get your head around it before you move to session windows. So I think what the context in which your question is being asked perhaps sits in the session window space, but it's a difficult, windowing is difficult. There are many moving parts, and to add to the complexity, we have got two orthogonal moving parts, trade and market data. Both are unbounded. So I would start with fixed windows, get my head around that concept before delving into the more complex areas of session windows.
And this is completely right. This is something you evolve as well, no? I mean, like, you go for a state where you can't do anything in this because, you've basically got some restraints, be that the size of your data center or be that the complexity of the system that you're working with. So the nice thing about the Beam model is that the semantics that you're using to describe the windowing, the triggering, that part, are separate from that, what is the function I'm performing. So if you get that part first, like first of all, you do like your global window, you do a batch, and you say, right, go and calculate this, get the part working with the quant libraries, maybe have some fun with the numerics along the way. And then once that's all running, then you can start saying, oh, like, what can I trigger on? What data do I want to actually refresh on? Now, that may be something where you say, essentially, I'm going to trigger every hour, or I'm going to trigger every 5 minutes, and I'm going to have here like a refresh of my market data every, so often. Or it can be something where you're literally handling these two streams, orthogonal streams at the same time, and then you're going to get into like, what am I actually calculating now? What data is in this pane that I'm actually, working with?
it is worth noting that Dataflow is really suitable. If you're starting to look at the microsecond, nanosecond space, it really doesn't fit in that space, right? This is not high-frequency trading system. This is high-speed risk, not high-speed risk. So, if what you have to consider is, what is your moving part? If your trade population is relatively slow-moving, and your market data is moving more rapidly on a tick-by-tick basis, maybe you window that part, and the side input that Robert mentioned is a way to broadcast the same data to all the cores. If you're using 4,000 cores, you want to broadcast that data. The side input concept is to broadcast that data, and the shuffling and all that other mechanism is taken care of for you by Google Dataflow. So you really have to break your problem down into its most basic parts and start there and then build your way up. I would suggest.
Cool. Any other questions? Yes.
We go to slide 25.
Slide 25. So I guess there are a few elements here. I mean, the number of workers you're using, the type of disks that you're using, we provide different options there. You don't have to work with disk. You could do this all in memory as well. But essentially, I think if you consider the amount of things that you're trying to calculate, and you think, okay, this is happening, it's not just one thing. I'm not trying to get like the lowest latency on this one thing. I'm trying to get a high throughput. This was not actually an impediment to that throughput. So it was an easy way of abstracting it and saying, hey, I've got a problem here because this thing is just spewing out like whatever, because there are some libraries involved there that just happen to throw everything on standard out. We didn't want to go in there and mix up with all those libraries. So we said, like, okay, let's just focus the output from my piece, put it onto the disk, pick it up again. And if you think about all that happening in parallel together, it wasn't a huge impact. I think that you switched from like spinning disk to SSDs at some point.
So curiously, I think Fred talked about streaming I/O before we used the disks paradigm. So when we tried 2 million swaps with the streaming I/O, and then we switched to disks. The difference was, I think we were using a fixed set of cores, so it was 28 minutes for those 2 million swaps, and it was 28 minutes and 30 when we switched to disks. So we were quite surprised how the effect of switching to disks, we thought it was just going to tank in terms of its performance, but that was not the case. And this is because it's shown in imagery as a disk, but it's actually the local local disk attached to that container, wherever that Docker piece is running. It could be the /temp space in there. It might be in memory. We really, you're in the virtualized world now, so you really don't know what is being used. The /temp is that really disk, or is it not disk? Right?
And it's worth mentioning as well, you have monitoring tools. So if your IOPS are too high for the spinning disk, you can switch to SSD, things like that. And again, these are all options. So they have nothing to do with your programming and your code, which is a cool part.
Another thing to bear in mind here is that if you're, Raj mentioned, if you're running in batch mode, with Dataflow at least, this is again a choice of the runner, but with Dataflow, if you get 4 errors, it will just say, hey, that's enough, we're going to stop this. In streaming mode, they would just cycle. But let's say that one of those workers goes down for whatever reason, some reason, and then Dataflow will take care of bringing a new worker, and it will bring it to that disk as well. Mm-hmm. So you could actually think about here, like, okay, let's say, if you're doing like the simple swap options, this was like what, 200 milliseconds or something. It was very
unbootstrapped. This is the piece we didn't go into. So because bootstrapping is happening off the interest rate curve, the first time you do a swap, the first swap is about 450 to 600 milliseconds, and then so if you start bundling your swaps in micro batches, so instead of making 1 trade per out of process call, you start giving it 4 or 5 trades. The subsequent swaps, because all the interest rate curve, the amount of market data is fairly small, so everything is bootstrapped. The following swaps were taking around 30, 40 milliseconds per swap. So when you do it across 6 or 7 in a micro bundle, you would do that in 700, 800 milliseconds. Yeah. So your total, that's where the scale out time that I showed flattens out. because that initial bootstrap is the way the Quant library works currently if we were using QuantLib. So this is where you have to start experimenting with your data structures and the way you serialize. You could serialize your market data up front and send it so there's no bootstrapping happening. These are the choices you can experiment with.
I mean, you essentially have a checkpointing mechanism here if this goes down or that goes down. So that's something you can also play with and say, hey, you know, is there a value? Like when I'm running these calculations here, like how much data do I actually need for that calculation? How much time does it cost to get that data prepared and ready? So these are things I would encourage to look at. Again, if you want to use JNI and just go straight over, that's also an option.
And it's really about you trying to understand your analytics, the way it interacts, and get a feel. You know, when you start running it and you start playing with the various parameters and you start moving stuff around, you get a feel for what works, what doesn't work. You get to an optimal point, then you can start looking at what can I change in my libraries to get this even faster, right? So it's an experimentation, it's a process, and that's why I think the Flink piece is cool, because you can do it on your machine with a small set of trades and start looking at that stuff without doing the cloud bit first, right?
And again, you mentioned this is not high speed, this is high speed. So this is not just used for risk. I mean, you can use this for whatever you want, and you don't have to do this out of process calling. I mean, if your libraries happen to be in Java or you're using Python, you could skip this part completely. The reality is there's a lot written in C++ out there, so we should be able to handle that, you know, and this is how we're proposing to do that in our experimentation. But I'm losing my train of thought a little bit. But what I wanted to say here was, come back. No, gone. You'll come back in a moment.
One minor question about this. C++.
So this is external to that container.
So yes, that one is JNI, so it is a Java.
So it's still got the Java
Yeah.
wrapped
Yes,
around it.
But the next one, this
if you
one
go
is
here,
Oh, right, okay.
yeah.
if you're doing protobuf, then it's a C++
Yeah.
process.
So I mean JNI because you're passing that Java object essentially, but here because you abstract with once the realization this is an interface, then okay, what serialization medium format do I have out there, which is language agnostic, and that's basically what we created protobuf for.
So yes, right. Your C++ layer effectively becomes an interface. So all you're doing here is wrapping it with a main, but you can also wrap it with JNI as well, and then it's called the same interface method. So that's what we were playing around with, and then we realized actually it's just much faster and easier with straight C++. And again, goes back to the testing, right? So rather than this big cumbersome sort of system that you have to deal with, all of a sudden you just have your executable and you can debug it straight in. So it was really cool.
I mean, it's also a question of journey, right? If you've got JNI today, because that's how you communicate, you can leverage JNI. So you don't have to change the whole world on day one because you're moving to this. You use what you have, you get it going, and then you start making the changes. So you don't want to switch to protobuf on day one. You don't want to change the whole world on day one. So you evolve that process. And we went through that exercise. You know, we went through that evolution over the months. And that's all we're trying to bring out, is that it's the way you decide you want to do it. There's no prescribed method. There is no set standard. It's how you do it.
I think the really key thing here was about separating out those responsibilities. So there is a piece here of actually, you know, having the quants work on their code and saying, right, you've got your code, we provide you this interface. There's a piece here of actually how do you orchestrate that data, and then looking at if you're going to move to a streaming space, like what data I'm actually sending out here, what are you calculating for me? And then there's a piece of how you integrate with the other systems, which is that, you know, another separation where you're saying, you know, I don't want to be inflexible that I have to work with this type of storage. You know, given a change over here, I want this still to work for me. So it's really kind of breaking this down into something that we could have clear responsibilities in a very, very complex environment, I must say.
Because you might be stitching your market data from a relational database. So you're making an SQL query, you're stitching that data up together, you're then passing it to the C++ layer. To us, that is really feeding the pipeline with data. It's not what the quant would be interested in. So he'll say, here's my data structure. I want my market data defined in this structure. Once you've given me that structure, I'm going to wire the pipeline, you know, because I'm going to do X, Y, and Z, and then I'm going to give you the results out. So it is about, it kind of
plumbing.
It is the plumbing, and it's about the separation of the plumbing. So, you know, IT are the plumbers, and if you want to look at it that way, right?
That's all right. I can live it. Hi. The question was about, you know, how do I test this? You know, how do I make sure that what I'm doing here is actually reproducible? I think that was the short summary of the question.
Yeah.
That one.
So yeah, that is actually the beautiful part about this is that your protobuf, so you can write tests on the Java side, the IT side, that are designed. That's your expected output from your process, right? So if it doesn't match, you fail the test, right? Conversely, right, on the C++ side, that's your input protobuf. So again, the same protobuf is used on both sides, if you see, and that becomes your contract, right? Again, it's very simple in that sense, right? And when one changes, so if the C++ side, you say, oh, I want to tweak this parameter, I want to use a different optimization flag, I've just got my new Intel compiler and it's got this new flag here, I want to try it, then you have to create another protobuf here to test, right? You pass that protobuf back to the IT side, and again, they have to match, right? If they don't match, obviously, then it's, you know, fair game for everything, right? But
So just before we move on to the next question, I think an important part here is, you know, understanding what data you're going to send across. But because you have this separation here, you can kind of, you know, work that out together and say, hey, you know, this is what I'm going to generate for you. You know, is this what you're expecting as input? So you can check that. You know, you run your code and give me an output. Is this what I'm expecting to receive from you as well? So it's that separation. I mean, coming back to the Windows or Linux, you know, compilation, yeah, that's an issue. You know, I don't have a magic wand for that.
It doesn't have to, I mean, I'll play devil's advocate. It doesn't have to be protobuf. Your contract could be XML for all you care. Your protobuf is nice. Protobuf is not without its limitations. So inheritance models, you will struggle with protobuf. So you know, it's not a silver bullet, but it is damn sight better than everything else that you currently have. So
this is functional programming. You should really kind of consider if you want to have like big inherited data structures going through as well. So there's another question. Yeah, the question is why protobuf opposed to XML or JSON? Well, I mean, like, as opposed to, let's say, a class that you're serializing, for example, a Java object, yeah, using Jackson, that would be an issue. Then you would need to use JNI. So you couldn't just pass the C++, so you wouldn't have that clean interface. But if you're working with something like a JSON or an XML, well, you could do that. But these are the heavier, let's say, serialization formats, and you need to go and implement them in both languages here. So you need to implement some deserializer and serializer on the Java side, and again on the C++ side. Now that's not to say that not all these programming languages and libraries don't have that for you, but protobuf, and again it's a choice, but protobuf actually provides you with those bindings. So you can define your contract, and then you can create the serialization and deserialization classes for both of your systems, both of your languages. And protobuf is really a very, very lightweight. I mean, like, to give you an idea in terms of looking at, you know, something like Avro, which is already binary, and looking at protobuf, you can expect, you know, up to like a 20x improvement in terms of speed. So
I think, yeah, that is so it is a distraction. We're not, you know, this is not about protobuf. You can do it in XML, but if you're doing it in XML, then you will have to parse it on the C++ side, and then feed your C++ objects with the parsed XML, right? So you'll have a SAX or a DOM parser on that side. You're going to pass the XML here. You're going to parse it on this side. That protobuf just allows your C++ objects. So if you pass an int or a string or a primitive date time, it simply translates from the Java space to the C++ space, or Java to Python, Python to C++, C++ to Go, without you having to do any of that overhead. You can physically do all that mapping and do all that. So in the sense your question is right, it's a distraction. It's not what's causing the system to work. I mean, Beam will work even with XML or with JSON.
But let's have a quick look at your results slide for a second.
Can I just add one thing quickly? Yeah, it's the consistency of the programming style, which is very important, because using 2 or 3 lines, you can both serialize or deserialize that object. When you look at the code, they look almost identical in C++ or Java at least. And that's like very easier to use. It's comforting, you know? Like, you're not looking at, like, for instance, if you're serializing in JAX-B on the Java side and then using maybe Boost on the C++ side. These two things look completely different, right? So when you're looking at the code, you're thinking, you got to really think about it. Whereas the protobuf style is very consistent across both. Yep. The API, the calls are very consistent. So if you try it out one time, just do one simple one field or two fields, it'll look almost identical. And again, the serialization itself is one call or maybe 2 or 3 lines. And then you have the same object in the different language. So it's really interesting to see that.
Yeah, and I think Dataflow itself has got a lot of optimizations for dealing with different serialized formats, be them heavyweight such as XML or lightweight such as protobuf. And if you look here at the difference in the results between Dataflow, so essentially here we're looking at Dataflow with JNI and XML versus protobuf. There is an improvement to be had with protobuf, but it's not as dramatic, especially at the lower end of the scale here, as we see with Flink over here. So Flink perhaps doesn't have all of those optimizations for those the XML objects. So you're going to pay a heavier price because essentially those serialization, it's heavier.
I mean, remember, you don't have dark fiber and all that kind of stuff in your data set. Maybe you do, but generally we don't have all that whiz-bang kit in our data centers. So you just buy commodity blades and you buy commodity, you probably have 1 or 10 gig switches. And so when you start looking at your infrastructure, and this is a good example of that, where you're running a box standard XML process versus protobuf, even when the networks are not optimized for shuffling protobuf streams around, we were quite surprised to see that, the remarkable improvement you get, that kind of differential you get by switching to protobuf.
Yeah.
So, and that's the only reason why we mention it a lot, but you're right, you don't have to go down that route at all.
And I think it's also worth mentioning within the Beam model itself, so the actual functional programming layer, it depends what kind of work you're doing there as well. But as you're passing between those functions, you're passing those classes between functions, you can also choose, how do you serialize those for classes. So you can go for standard Java serialization. You could also go for Avro, which is quite simple because it's just an annotation on the class. Or you could go for protobuf again, which is a little bit more work. You have to go and create the bindings, but you get basically, less being communicated between those different systems, so you get that performance gain again between the different workers who are communicating. Yeah. Any final questions to? One more. Yes. So the question is here. So the question started off with, in a perfect world, having just one runner, or now Beam supports multiple runners. And maybe those runners don't implement all of the features that Beam has to offer. So first of all, if you go to the Beam website, you can compare the different types of runners, and they will tell you which things have been implemented and which haven't. So there's functionality there, and some of that functionality is dependent on the underlying hardware. So that's something you need to watch out for. That could be in how they deal with different types of windowing strategies. It could be to do with, we can pull it up even, but we just need to go to the Beam website.
Splittable do funds.
Yeah, splittable do funds. It might be that there's some new functionality in Beam that hasn't actually been built into that runner yet, so they maybe lag in that. So I think it's good to actually go to the website, follow actually, and look at which runners you're using. We work with other companies to make sure that those runners, get as much parity as possible, because essentially, Beam has given us this abstraction that we want to have. Cloud Dataflow is never going to run anywhere apart from in Google, because essentially it's our infrastructure and all the systems that we use underneath to actually make this as managed and as fast and as cost effective as possible. But working with companies like Data Artisans, for example, with their Flink runner, that's why Flink's such an attractive runner for us, because they're trying to give something that you can run, on premise, for example, and get a very similar experience. So I think if you're in the business of creating runners, then it's good to try and stay up on feature parity. For anyone using it, I would say have a good look at the Beam website and actually see which runner is actually at which stage, and then I would say, well, when you're choosing which functionality to implement, beware of implementing something that's only supported by one runner, because that might give you a problem, unless you particularly need that type of functionality. Any last question? Anyone else? Well, then I think we will round up and move to the to the cocktail area.
Thank you very much, guys.
Thanks,
Thank you.
Thank you.